Hello everyone, here's JJ. So we only have 2 chapters left. One is differentiation, one is integration. So today we will talk about differentiation. And I mean, if we want to learn this last two chapter, is something really important. If it is something really helpful if you understand how limits work. But if you don't know limits, it's fine, because when I explain, I will skip limit this topic. But if you know that, it's really helpful to help you to understand it. And okay, let's go. Go. So do this question. This question is really helpful for you to do some question about differentiation. Let's go. Skip about it. Don't worry. So, I mean, strictly speaking, the value of a derivative at a certain point means the slope of the tangent line of a function at a point on the graph of this function. Yeah, I mean, it's the easiest way to let you understand what is derivative, because I mean, yes, tangent is easy to make a tangent. I mean, if you have a tool like GeoGebra, it's really easy to draw a tangent line of a function at a point. But actually, if you really draw a tangent of a function at a point, it's not really easy, because how do you say that? The gradient of a curve at the point is the gradient of the tangent to the curve at the point. But when you draw it, you have to make sure that the tangent of the the slope of the tangent line should equal the slope at this point at this function. I mean, maybe it does not make sense, because you cannot say slope at a point, but actually it means something like that. Look here. So actually, tangent is how you draw tangent. We have to do something like that. So here's an example function, and here's a point. Here's the point that we want to know the slope at this point. So now we have another point on the graph. So we move the point on the graph, and we let it really near to the point which is stable. Yeah, so let's see here. So I mean, when we really near here, we will find that the line change really slow, right? I mean, even though at that point it's not make sense to draw a line, but I mean, if we continue this process, but if the point never achieve this point, but really near, I mean, if this point approach the point which not move, then we can get the tangent line at that point. Okay, I will make the simplified video about this process, because my explanation is not really good right now at all. But yes, so let's continue. So this process you can also use calculating to help you understand this process. So here's an example. On the graph y equal x squared, a chord is drawn from P for 16 to the point QXY. So the thing is, I mean, you can put a x here and you get y. So you can make a chart about the coordinate of Q, and then you can calculate the delta x and delta y. Then you can calculate the gradient of PQ. So I mean, you let x approach 4, then it also means that y approach 16. So approach, this word is really important when you learn about differentiation and I forget the name, but yes, I mean, you have to use this word. You cannot say achieve, because in math, in those topic, you cannot, the point never achieve, because if you really achieve, it's not make sense, right? So after you calculate, you will find something really interesting, because the gradient of PQ will keep like will oh my god. Convergent. You'll find the result of gradient of PQ will be convergent. For this case, it will keep like 8. So actually, if you really use a tool to find the slope of the gradient line at P of y equal x squared, this function, the derivative at that point will be 8. You can try. I mean, it's something, maybe it's a little bit hard to understand why is that work, even though it's not really strict that PQ when Q at, oh my god, even though P never achieved, even Q never achieved P, but why we still can use P, the gradient of PQ to express the derivative at point P. But I think you guys can get it. Oh my god, yes. The process of finding the gradient of a curve is called differentiation. Each point of the curve can have a different value for the gradient. The function which gives the gradient at any point on the curve is called the derivative, slope function, or gradient function. There are several different notation for the derivative. If the curve expressed as y in terms of y in terms of x, we should write the derivative as dy over dx. However, there's nothing special about y and x here. If the graph of variable g against the variable t, then the derivative would be dg over dt. So, and also if the function being differentiate is fx, then the derivative is fx. Okay, it's something like that. I will use another simplified video to explain the process I do here, so don't worry about it. Let's continue. I mean, now okay, so why we need derivative? Because something here. If when x increase, fx increases, the function is increasing. If when x increases, fx decrease, the function is decreasing. Of course, but look something here. If when x increasing, fx increases, so that derivative of fx will more than 0. Oppositely, if when x increases, fx decreases, therefore the derivative of fx will less than 0. So the thing opposite is also makes sense. So if you know that the derivative of function fx at one point is negative, it means at that point the original function, if derivative at one point is positive, it means the original function at that point is increase. Oppositely, if derivative of the function at one point is negative, it means at that point the original function is decrease. So it also makes sense, because I mean, according to definition, delta y over delta x, if f increase, fx also increase, it means it's something like that. So the delta y is positive. The delta y is positive, and also the delta x is also positive. So derivative obviously is opposite. But if the function is decrease when x increase, so the delta y will be negative and the delta x will be positive. So the derivative of the function at that point will be negative. So it makes sense. I will use something here to explain. Okay, I will use tool derivative at that point and do something here. So obviously the coefficient before x is the gradient or the gradient of the gradient line, which also express the derivative on the function at one point. You see, here obviously the function is increased and the derivative is positive. At that special point, I think here is a special point, the derivative will equal 0. But now, I mean, it's hard to show because I don't know what GeoGebra is not really continuous. I mean, I cannot find this point. Oh my god, not here. But you see, when the function decrease, the derivative is negative. So yes, I mean, it can help you to understand it, right? Okay, let's go. Let's continue. So if the question asks you, in which the function is increasing, yes, the answer is this. So also you can say that the derivative of function when x less than 1 or more than 3, the derivative is positive, right? It also makes sense. At that point, at those range, the derivative is positive. At that range, the derivative is negative, and at this 2 point, the derivative are 0, exactly 0, because it's not increased and also not decreased. At that point, it's flat. The derivative is flat. So sketch the derivative of this function, so it will be really easy. So obviously at that area, the derivative is positive. At that area, the derivative is positive. At that 2 point, the derivative is 0. At those range, the derivative is negative. So the derivative function will look something like that. Yes, here's color to help you to understand it. Increase, positive. Decrease, negative. Increase, positive. 0, 0, 0, 0. So it will be something like that. So maybe from this graph, I think maybe somebody can guess how to get the derivative of a function. Let's keep it as a secret. Hello? The graph. As what I said, derivative and increase, decrease, the condition always can change. We can change the position of condition and result. So now we know the graph of derivative function. Therefore, we can know that original function at which range is increased and at which range is decreased. So derivative here and here is positive. So it means original function at those two range is increased And also, this two range, the derivative is negative. So in original function, the graph of original function, those periods will be decrease. So probably it will looks like something like that, because it is, so it will be like something like that. So obviously is x equals 0, x equal 2, x equal 4. My sketching skill is not really good, but you guys, you can see negative period decrease, positive period increase, negative period decrease, positive period increase. So something like that. Yeah, they use same method as here. Use color, use different color to express. I mean, remember, from from the graph of derivative function, you have to take care of positive and negative. But I mean, if you want to draw derivative graph of a original function, you have to take care of increase and decrease. Okay. My English is still abstract. I don't know. Can you guys understand? I'm so sorry. Oh no. Now is something really fun. So now we have to learn how to find the derivative of function like 8 times x to the power of n. So here we know that. So here's a conclusion. If fx equal x to the power of n, where n is integer, then the derivative of the function will be n times x to the power of n minus 1. But do you guys know how to prove it? I can show you. So I mean, it's like, so do you guys know who invent a derivative? Yes, it's Newton. And Leibniz. But I mean, original derivative is not really strict. It's not really serious. So that's why somebody said it's not. Somebody against it thinks math is not really strict subject. But yes, I mean, I can use original way to prove it. It looks really obviously. So we know that. Guys, does that make sense? Not really. Remember, even though I will not talk about limit, but now I will say delta x will near to 0. So I mean, this thing looks not really friendly, but actually it shows that. So x0 is the point that I want to calculate the derivative at that point. Is not, grammar is not correct, but here x0 plus delta x, it shows that it is a point that's really near to x0, but with distance delta x. But I will let delta x approach 0. It means these 2 points will be really near, like from this point, like here. So from this point to this point, this point to this point, this 2 point to this point. But yes, so we know that it will be something like that. Maybe, I mean, after we we meet each other again. I can explain it face to face, but no worries. Then, I mean, the something under will be something related to delta x, and something up. I mean, guys, maybe you guys can know that you know that we can expand this, then we can get something related to really long. But I mean, after we expand this, we also have a x0 to the power of n. So this two will disappear. Then we will get something like that. Continue. I mean something after. Yes, let's continue. It after we expand, I mean we'll have something left, and then we divide it by delta x. Then the first term will be this, and something after, because all the term have delta x. So we no matter how a delta x to the power of what, we can get something related to delta x times something. If we don't have to care about something in here. Why? Because remember we have limit, we have approach. Obviously, when delta x approach 0, this whole thing will disappear. So the result will be this. So derivative of this function obviously will be this. I will take a photo of this picture. No worries. So I mean, yes, I mean it's still hard to understand, but yes, let's do some example question. I mean, I find that it's really hard to explain something online because my English is really bad, so that's sometimes I cannot explain immediately. So, but no worries. Let's do some example question. Let's use the knowledge first. So, if we know the function fx equal x cubed, find the derivative. So the derivative according to the conclusion, we know that the derivative will be 3 times x squared. For this is same. It will be -4 here, -4 minus 1, -5. So it will be -4 times x to the power of -5. So if we have a coefficient in front of x to the power of n, then if it is a real constant, of course, then the derivative will be, yes, it's just like, so if we just put the a in front of x to the power of n as a coefficient, then the derivative is also we just put a in front of n times x to the power of n minus 1, right? So yeah, it's just something like that. If you want to ask me the reason, we also still can use this. I will take a photo. I will take a photo of this picture and how to prove this one with a coefficient. Also, so here's some example, but I think you guys can do it by yourself. So here's a question. Here's something about the derivative of fx equal 8x to the power of n plus b times x to the power of m. So I mean, if we have many this kind of term where a and b and something else are real constants, and the power of all things about x is also integer, then the derivative will be. So actually, I can tell you guys something like that. So if you have something here, okay, we use fx plus gx. If you want to know the derivative of two function plus or minus, then the result will be the derivative of first function plus or minus derivative of second function. Don't ask me why right now, but just remember. Actually, you see, first term is 8 times x to the power of n. So the derivative, the first term of derivative will be 8 times n times x to the power of n minus 1. So second term is b times x to the power of m. So the second term will be b times m times x to the power of m minus 1. So yes, here's something can help you to calculate some derivative of some really long function, like something like that. So for example here, then we know that the derivative, so actually we know according to something here, maybe you guys cannot will think about what's the derivative of constant. So actually you can write constant as such form. For example, minus 2 as negative 2 times x to the power of 0. The derivative of this term will be 2 times 0 times x to the power of 0 minus 1. So it will be, no matter, it will be x to the power of negative 1, but no worries, because we have a 0 in front, so it will disappear, this term. So the derivative of this function will be 7. Oh yeah, so if you want to know the derivative of this function, actually, you have to expand this as the form we know, something only related to x. What I mean is so actually after we expand it, it will be better if we write the form like that. Because x is a variable, so the derivative will looks like something like that. So yes, that's why we have to practice this, because we have to simplify this form to the form like this. So yes, first let's simplify it. We know the term, it will be half of x minus 3 times x to the power of negative 1. It's everything like coefficient times x to the power of something, and the relationship between each term will be negative, or will be minus, or plus. So according to the conclusion, we know it will be something like that. Okay, here's some example. Calculating the gradient at a given point. Yes, if we know how to get the gradient function of our original function, then we just put the x we need in the derivative function, then we can calculate it. For example, this case, the derivative of this function is 15 times x squared, and we want to know the gradient where x equal 2, then we put x equal 2 in the derivative, then we know the gradient is 60. Same here. But here is something a little bit changed. After we calculate the derivative, we know that it's like 3x squared plus 12x. And let us find the value of x for which the tangent to the graph of this has the gradient 15. So we let the derivative equal 15. Then we can solve the equation. Then we know x is equal -5 or 1. And analytic approach to find the equation of a tangent. So here's a result. Actually, how can we get it? It's related to something in chapter 4. So I shouldn't skip chapter 4, but most of stuff in chapter 4 is difficult. It's too easy for you guys, because you guys have already learned that with Miss Plus or Mr. Veda. So, and I will explain this form. How can we get this form later? And also we know that if you want to find the how to say that, the normal to a curve. The normal to a curve at a given point is a straight line which crosses the curve at the point and is perpendicular to the tangent at that point. So tangent is here, normal is here. I mean, these two are perpendicular. According to the knowledge, I think everyone know that. You can use the fact that the perpendicular lines m1 times m2 is equal -1 to find the gradient of the normal. So we have something here. No worries, I will explain later in a individual video. So actually, guys, that's all. So I will make 2 simplified individual videos and send it in just in the group chat. So no worries. No worries. Oh my god. I really like teach everyone face to face because it's easier and it's so much fun. Oh my god, I don't like video teaching. Only so bad. So bye guys.